work through problem 4.9 from Taylor's Classical Mechanics, Chapter 4. And this is a question on potential energy and conservative forces. So for part A here, we have the force exerted by a one-dimensional spring fixed at one end is going to be negative kx. X is going to be the displacement of the other end from its equilibrium position. So we're going to have something that looks like this. That's our equilibrium. And we're going to have another spring that's displaced and somewhat stretched out. And the distance between the two is our x value. So that's the amount we're stretching the spring. Now it's saying to show that the corresponding potential energy of the spring is 1/2 kx squared. And we can start the same way that we usually do. We're assuming the force is conservative, which it is. And we're going to show that the spring's potential energy is 1/2 kx squared. Of course, depending on that k value, the spring constant. So we can start with our force. We know our work in stretching from our initial position, our equilibrium, to x is going to be the integral from x naught to x of negative kx dx. And that's going to be negative 1/2 kx squared minus x naught squared. Assuming that our equilibrium is at a zero value, the potential energy at our equilibrium is 0. Our work of the spring in stretching from one point to another is going to be negative 1/2 kx squared, in which x is the distance that we stretched the spring. Knowing that the force is conservative, we know that our potential energy is going to be the negative of our work. So we find out that the spring's potential energy is 1/2 kx squared, which is what we wanted to show. So now we're changing things up a little bit. For part B, we want to suppose that the spring is hung vertically with a mass m suspended from the other end and constrained to move in the vertical direction only. So we want to find the how much it's going to stretch based on that mass, and also going to be based on the spring constant, of course. And we want to show that the total potential energy plus gravity, so the spring plus gravity, the total, has the same form of 1/2 ky squared if we use the coordinate y equal to the displacement measured from the new equilibrium position. So we're going to make a new equilibrium position wherever our mass takes that equilibrium to be. We're going to find an equation for that, where that's going to be located. And we're going to redefine our reference point so that at y equals 0, that's going to be our new equilibrium point. Our potential energy is going to equal 0 at that point. So let's draw it out here for part B. We're going to have a spring vertically suspended. It's going to look something like this. We're going to have a mass on the end, mass m. We know that the spring is going to pull up with a value of kx. The negative above in the spring force is just displaying that it's going the opposite direction. It's going to oppose the stretch. So that's taking our positive direction to be this way. To the right in our picture up above here, we're taking the positive direction to be this way, so our force acts in the negative direction. Here we're just taking the positive direction to be upwards, and our force of gravity is going to act in the negative direction. So at equilibrium, we can call our equilibrium point, so whatever this point here is, x naught, and at equilibrium, kx naught minus mg is going to equal 0. The forces are going to cancel each other out at equilibrium, and the system is going to be at rest. So using this, we can find an equation for what our x naught will be. Equals mg. That means that our x naught is going to equal mg over k. So that's the first part of part B. It's the first thing they're asking us. Suppose that it's hung vertically. Find the extension x naught of the new equilibrium position with the suspended mass. Okay, now we're going to have to show that the total potential energy is going to have that same form. So this is going to be our x naught value. Now, if we take this to be x naught, the value here is going to be x all right, we're going to take this to be our x naught. So this is the unstretched portion actually here. We're going to take a portion here to be y. So our x is going to equal x naught plus y. It's going to be important here in a second. Our total potential energy at this time is our 1/2 kx squared from the spring's potential energy minus gravity's potential energy. So we know that x is going to be equal to x naught plus y. So u is going to equal 1/2 k x naught plus y squared minus mg x naught plus y. This is going to work out to be 1/2 k x naught squared plus 2x naught y plus y squared minus mg x naught minus mg y. Go ahead and distribute this out. From this point, you can see here, we're going to want this 1/2 ky squared. That's what we're trying to show this is equal to. So pull that over here. Now from these two terms, we can factor out a y. We're going to be left with kx naught minus mg. And that leaves us with 1/2 kx naught squared minus mg x naught. Now, this right here represents our potential energy at x naught. And this represents the potential energy of gravity at x naught, which is the stretched position after we have that mass suspended vertically from the spring. This is the position we're going to stretched. Based on that, we know that this is going to be some constant here that's caused by the situation of the spring. So we don't have to actually regard that for this example. And then we're just left with this portion right here. Further up here, we determined that at x naught, the spring force would cancel the force of gravity, which is exactly what we have here. Kx naught minus mg is going to equal 0. So this whole term will go to 0, which leaves us with the total potential energy equaling 1/2 ky squared, which is what the question is asking us to show.